Today we mark the beginning of the transformer journey. So attention is all you need is where this whole story of transformers started. Some people call them transformers, some people call them LLMs, large language models. They go by various names, or some people call them just generative AI, because the basic instrument of generative AI is LLMs, is transformer. So today what we will try and understand is what is a transformer, how does it look, why does it do what it has to do, and how is it structured from within. Okay, we will start with that. Now I have just picked up a paper which was not given to you, but this is just a mathematical paper. We will probably send it to you if you are interested. It's basically doing it through maths, because I thought we could use that as a framework to understand. And then we will talk about, while we are going through this paper or this article, I don't think this is a paper. The interesting part of this article is there is only part 1 available, part 2 is not there. Okay, so we are the part 2. So that picture is very symbolic. Most people who try to understand attention is all you need are like that cat. They start weeping when they start reading the paper. So it's transformers is a difficult journey to start with. So I hope you are not going to weep or you are not going to cry. You are not able to understand. See, it's like this. Transformers, everybody knows, is at the at the beginning of a big story which is generative AI, and it is very mandatory, or it's rather imperative, that you grasp this paper to a large extent, or grasp this concept to a large extent. So I'll go very slow and try to get most of the ideas in, and then let's see if you have still not got it. Probably we could have towards the end a follow-up session if you have not got it, but I'm hoping that you will get it. So there is 2 parts to a transformer as it was visualized. You see the left side, that is often called the encoder part of it. In fact, the paper labels it as an encoder. And the one which you see on the right side portion, it's called the decoder. Though an encoder encodes and a decoder decodes, it is important to understand that actually the encoder and the decoder are very much alike. They are designed to be similar. The key part to understand in a transformer is the one which is in that rectangle. You are seeing that rectangle on the left, that rectangle which has the following. So here we are. So I would like you to focus your attention on that rectangle. I know there are many rectangles, but the left side rectangle, where we see in that rectangle 2 major pieces. One is called the multi-headed attention, and the second piece is called feed forward. And feeding that at the lowest point, you see there is something called input embedding. And then we have the same story repeating kind of on the right hand side with a little change, but if you understand the left, you understand the right also. And then you have n into, that is not nx, some of you will think it is nx, it is n into that many. That n changes from GPT-2 to GPT-3 to GPT-4. GPT-2 started with 24, GPT-3 went to 96, GPT-4 went even higher. The architecture of GPT-4 is not shared in open domain, so we don't know what is n, but there is an n, and it really doesn't matter how many n's are there. As long as you understand what each portion is, n of that is similar. So just to give you an understanding, typically in a GPT-3, this n is about 96. So what you have is, on the encoder side, you have about 96 such blocks, okay, and each of this block we call it a transformer block. The one which is n into that portion is called a transformer block. And if you will, the transformer block consists of essentially 2 parts. What are the 2 parts? There is a MHA block which is called multi-head attention, and there is an FF block which is called the feed forward block. These are the two blocks, and to understand attention architecture you have to understand what these two blocks do, what these two building blocks consist of and what is their function. Okay. Now let us start the journey from the bottom. Okay. There is something called input embedding. So if you are given a sentence, what does ChatGPT do? Generate the next part, whether it is a question. Normally you would ask a question or you would ask it to create a poem or whatever. So basically it looks at your whatever you have given as a prompt or as a query or as an input. So that is the input. So when we say input embeddings, we are talking of something else. So your input, first of all, unlike an RNN where your input is taken piece by piece, and that is why RNN is not very GPU friendly, there is not much parallelism there. Whereas the attention network will take the entire input, whatever be the size of the input, the attention will take the input, the entire input. So now how does the input look? Now typically the input, whatever be your sentence, is converted into a series of vectors. We call them series of input vectors. So let me just give an example. When is sunrise happening? Now I am just taking an arbitrary sentence. This sentence is not going to be used. So if you see this sentence, there are 4 words or 5. Forget even if you don't give this. So you have when is sunrise happening. Now when is a word, it's converted into a vector. Is a word, that's converted into a vector, and each word is converted into a vector. So this is called the first level of vectorization. Now this is a very important step which often the paper doesn't emphasize but just alludes to another paper, but let's spend some time understanding this vector. How does this word become this vector? So first of all, what would be a typical dimension of this vector? Now if you take, let's say, GPT-3 as a benchmark, this would be about 12,288 positions. So it would be a vector of this size, of this many dimensions. This is pretty big. 12,288 is the size of that vector, which when is converted to. Now you will wonder, why does when, simple trivial word, get converted into a vector with 12,288 dimensions? What is it that is so special about when? Let's talk about it a little bit. See, there is a lot of information. Okay, before that, this knowledge of how to convert a word into a vector actually doesn't come from this paper. It is not attention all you need paper, but as I said before, there is a paper in 2013 which is the classic paper, the seminal paper for word to vec, which is converting a word to vector. The algorithm, again coming from Google, was first proposed in 2013 and then it was refined further by many people, and today what we see is a refinement of that vector. So there is a lot to do with this vector. I'll try and elaborate a few factors about that vector. First of all, the vectors are created in such a way that they follow the laws of vector maths or vector algebra, which means what? I'll give you some examples so that you'll appreciate how that vector actually gets created. Okay. So the vector is such a way that if you look at the vector of the word biggest, if you take the vector of the word biggest and consider that, and then subtract from that word smallest, okay, or no, subtract, let's say, big. So you have a vector for biggest and subtract big from it, which subtract big means subtract the word big from it, then add the word small to it, add the word means add the vector for the word small to it, the vector it will come is the vector for smallest. That is not how it is created, but the way it is arranged is so happens, and these are almost close, they are not exactly close. I will repeat this again. So, the vector, if you take biggest, the vector for the word biggest, if you subtract as in normal subtraction, okay, vector subtraction of course. If you subtract the word big from it, from whatever is left, if you add small to it, the effect will be smallest, the same vector. So, that is a magic of how these vectors have been created. Now, at this point, does this mean that we are getting into the semantics of it? Well, kind of, but we have not ourselves put semantics there. It has so happened through training that these semantics are being obeyed. We did not train it for vectoral algebra. We did not train it to obey these laws. It is so observed that without following any laws, by feeding in a large corpus of information, the word to vec algorithm learned so much that it started creating the vectors in this manner. So, which is why I am pointing this out is, this is how systems have become automatically intelligent. We did not intend them to become so intelligent, but they became intelligent such that these laws were automatically obeyed. So, on the other hand, if you see, these vectors are so interesting. Now, if you add the vector which gets added to dollar to make it dollars. Now, dollars and dollar are two different words. So, the vector which you add, or rather if you subtract dollar from dollars, are you getting me? You get something. Now, if you add that something to a mouse, you will get mice. You are getting me? By the way, I am hoping you know that plural of mouse is not mouses but mice, right? So basically that will happen automatically. I mean, I don't have to do that. That is also learned. Another evidence of a similar learning, you see how they have learned these vectors. The magic is in the vectors. If you take the vector for king, subtract man from it and add woman to it, you will get queen. Getting me? Now you see, I went from singular to plural. I went from smallest to biggest, and now I am going from one gender to another gender. All of this is happening in vector algebra. See the amount of work or knowledge it has picked up in this word to vec. This is nothing to do with attention, but attention is using all of this. Attention is driving from all of this. But this is very fundamental to understand. Now, this is where some of these old LLMs fail. I will give you an example of where it fails. You take doctor, the word vector for doctor, subtract man from it, add woman to it, you get, unfortunately, not doctor again, you get nurse. You are getting me? Take doctor, subtract man. From a king, if you subtract man and add woman, you got queen. But from a doctor, if you subtract man and add woman, you will get a nurse. Now, this is the bias, because the corpus on which it was trained, whatever the corpus which is available in the global network, in the web network or in the overall, there a woman in a medical profession is more likely to be a nurse than a lady doctor. So, this is bias. Now, models like GPT-3 or GPT-4, GPT-3 or earlier would carry this bias. Whereas, when I will introduce you Llama 2, Llama 1 or the original Llama also carries this bias. But when you come to Llama 2, by another thing which we will talk about in that session called reinforcement human learning. What Llama 2 has done is, by having a feedback loop, it has realized that gender bias is removed. So it is not just the system should be helpful, it should also be safe. Now gender bias comes under breaking of safety. I mean, there are many other examples I could probably give where this wouldn't happen, but there are so many examples in which gender bias is there. If you read more, you will understand more about this gender bias story. This has to go away. There are a lot of biases in our regular literature, and all these biases need to disappear. Some of these, through further training on the word vectors, have been able to achieve it. As I said, Llama 2. GPT-4, I am not sure, there are no statistics available how safe it is. It takes care of this problem, but I don't know on other gender or other safety norms how well it is doing, but Llama 2 is pretty good, and it has got rid of a lot of these gender issues. So that is about just the word vector and how important the word vector is in terms of its realization. I will give you another analogy just to help you appreciate how the word vectors work. So there is, for example, you take let us say Hyderabad, and the distance between Hyderabad and Telangana as a capital. If you add that distance to Paris, you will get France. Make sense? It should, right? So again we are going from a completely different domain. We never expected this to happen with capitals, but it has learnt all of this. So the word to vec is a important secret sauce of this whole working, and attention won't happen if the word vectors are not appropriately created. So now in the present example, just to appreciate the maths, what they have done is they have created a vector which is random data, but now you know that that's just an example, just to help you illustrate how the paper progresses. Initially, of course, we don't start with random numbers, but that paper starts with random numbers, or that article starts with random numbers, just to give you maths, because that paper is focusing only on maths. Okay. So when you say input word is converted into a vector, I am sure you will realize that there is a lot happening there, and it's not just some trivial algorithm which is doing it. It's a lot of learning and a lot of design which has a lot of learning. I wouldn't say a lot of design, but a lot of learning has happened in that creation of that vector or definition of that vector. It's not an easy story, and this story, remember, started in 2013. So there was 4 years of learning of these vectors before 2017 came along and this paper was defined. So going forward, we go back to the paper. Okay, so we have this initial input embedding. So I hope everybody is clear what is input embedding. Basically converting the words into vectors, that's all. Intelligent vectors, I will say, not just plain vanilla vectors, intelligent vectors. Now the second part, if you see there is something called positional encoding, which is, okay, now since we shouldn't go too far ahead, I think we'll go up a little bit in that paper and just tell you what is happening. So just the maths, go up, keep going up, keep going up. So he also starts with some kind of a corpus. So this is the corpus. As you can see, his corpus is only 3 sentences, not billions and billions of data. So we'll just follow his story. So can we go little down? So you have to compute a vocabulary size. Obviously for English the vocabulary size is the whole dictionary. He has taken a vocabulary size which is very small. Come down, keep coming down. Then obviously the duplicates ought to be eliminated, and okay, come down. Then the encoding starts. So first of all, if you take a sentence, whatever is the corpus sentence, there is some words given to it, some numbers given to it. They are just running numbers. Don't worry too much about it. Come down. The sentence he is using is when you play the Game of Thrones. Okay. Okay. Now here is where the thing comes. So now he is saying, he is showing you that in real life, using Google word to vec, when gets converted into a vector of 512. This was earlier. Now you do not have vector of 512. This was the GPT-1 where one vector became converted into 512 dimensions. Today, as I told you, in GPT-3 we have 12,288 dimensions. So this is, but does not matter whether it is 512 or 12,288, it's a matter of scale. So we see the vectorization. Now he is saying there that there is a paper called Google word to vec, which is what I was alluding to, which actually determines what should the vector be for when. Okay. So, but here he is just taking an example because he wants you to have easier maths. So if you see in his picture, if you look on the right hand side, you have when, forget about that phi, that is the cardinal number, the cardinal or ordinal number, forget that. Look at the vector it has assumed. So it has assumed a vector of about 5 values. Each word is a vector of only 5 values for him. Instead of 12,288, he is taking a vector of 5 values. Just to illustrate, you can also, why I brought this paper is you can play this paper with simple Python and see how it is happening. Just to get yourself a hang of how the attention is all you need. So that's what I found good about this. So it just each word has become a vector of 5 numbers. And I think all of us are clear, it's not 5 numbers, it's 12,288 numbers. Now, what you need to do is, every word in a sentence has a position in that sentence, starting with position 0. Somehow, the word has to be given a positional encoding also. It is not just what when vector is, but what its position is in the word somehow also has to be encoded in the vector. So how do you go about encoding the positional status of a word in a vector? Okay. So how do you go about doing that? Okay. So the way you do it is you have this and then encode the position. Now what the paper suggests that in order to encode position, again do some maths, and that's why I brought this article. It shows you clearly what the maths is going to be on a vector to encode its position. So the way it goes about doing it is, let's just scroll up a little. Now it is doing positional encoding or positional embedding. So what it does is each bit of that vector gets encoded. Each bit of that vector means each dimension of that vector gets encoded differently depending on the position of the word. Now there are two variables. Ruko. There are two variables. Now based on the, what are the two variables for a given word? For a given word, the first variable is what is the position this word takes in the sentence. What is the position this word takes in the sentence? For example, when is the sunrise happening or whatever, when is 0, is 1, that is a position, that is pause. Now within the vector there are so many dimensions, correct? So for the dimensions there is some maths which is there. So 2i, I stands for the dimension, which in his example will range from 0 to 4. In our case it will range from 0 to 12,287 because that is a size. So it will vary depending on what is the size. So now P odd is the positional encoding for an odd dimension, positional encoding for an even dimension. How does it get computed? Are you clear about the maths? Position is position in the word, position in the sentence. I is the ith dimension. So every word has, in his case, 5 dimensions. So every dimension what happens to that? If it is an even dimension, it will use the even formula. If it is an odd dimension, it would use an odd formula. Okay. So he has given the working of it below. Now then I will tell you what does this mean. So this is how the positional encoding works. So the P1 vector, after it has been positional, the P1 computation, you see on the right side for the first word. So even on even, what is the P1? Do you get even and P1? Even is on the left, P1 is on the right, and that computation which I just talked about is happening on each dimension of that word. Even is when, on each dimension of when the computation is happening. So that computation, once it happens, this is the number that you get, or this is a vector you get for even after it has been positionally encoded. So you have a positional embedding. What has this done? It has some way grasped the position and encoded it in the vector. Somehow we have to encode the vector with its position, because when occurring once is different from when occurring somewhere else at different part of the sentence. Now at this point, this is called positional encoding. Okay. Now you will have to understand there is one more thing which this takes into consideration, and somehow this it is highlighted in the paper, but in this article it doesn't seem to come out that well. When we do positional encoding, there is also, you have to understand that the word vector is not fixed. I am going to make a very profound statement. When you say I am having a word and converting it into a vector, don't assume that the same word will always be converted to the same vector. Never, because there is no hard and fast rule which says that this word should become this vector. It also depends on the context, and that's where the magic becomes even more interesting. Now I'll give you an example so that you understand what this means. In English, we have this thing called homonyms and polysems. I'll explain what they mean. Now homonyms is, typical homonym they give example is of a bank. So I went to a bank is, I look at bank as a financial institution. I went to the bank to draw money or to deposit money. You are referring to the bank as a financial institution, correct? So he was walking on the river bank. Now here we are not talking of bank as a financial institution, we are talking of bank as the bank of a river, and the road didn't have appropriate banking. This is something else. We are talking from a civil engineering perspective, that the road had appropriate banking. So, or the road was banked properly. This was a different bank we are referring to. Now these are called homonyms. They are same word getting used differently. So should the word vectors be similar? They should not even be similar, because they are different. On one side you are referring to a financial institution, second stage you are referring to a river bank, third time you are referring to something else. So the word vectors ought to be different, because they have to capture the essence of where it is used. So it is also the word which it is getting used in the context which matters. Now that embedding is also called the context, that also is part of the position embedding. Now it is not reflected in the maths, because he has given you a simplified picture, but that is captured again, because it is significant. Now these are homonyms. Now let us take an example of polysems. Okay. What is polysem? For example, I picked up a magazine and Joan works for a magazine. Completely different, not completely different, somewhat similar. I picked up a magazine, basically I picked up a magazine to read. Joan works for a magazine, here the magazine is a institution or a company. She works for a magazine. You getting me? Words are same, but they are polysems. Now here the difference between the two vectors is not that different. The word which is used, magazine which is used in the first sentence and the magazine which is used in the second sentence, the difference between the two vectors, because they are polysems, is not the same. There is also other things, like for example, the professor asked the student to do her homework. The professor asked the student to do her homework. Now, her here refers to the student or the professor? Not so obvious, right? The professor asked the student to do her homework. Her can also mean the professor. But generally, the colloquial interpretation of this is, generally professors ask the student to do their homework. Professors don't end up doing homework, correct? Now this is knowledge which has to come. Now this also gets embedded. The her in this sentence will be different from her somewhere else. Are you able to get? So again, this whole thing is between the input embedding and the positional embedding, this changes. This all thing gets absorbed and coming down. Now here this example does not capture all of that, because I think it would be too heavy to capture it at this stage. It just captures the position. But I am just pointing out, it is not just positional encoding, it is also the contextual encoding which gets captured in the word vector. The word vectors will carry of which sentence they are part. Okay. Now here they say already, that means the word is starting to look at its neighbors. You are beginning? Because it is determining its context in a very rough way. Though the attention mechanism has not kicked in yet, we are still at the beginning of the mechanism to start. Even then, because the sentence is being analyzed and the word is being taken individually, but at the same time it is looking, because of the positional embedding and the context embedding is not captured here. It is looking at what is in the rest of the sentence. The rest of the sentence is also having a bearing on my vectors. So what happens is, the positional vectors, or which have been computed, and the original embedding vectors, they get added. This is called concatenation. So concatenation in normal parlance we mean one next to other. In this parlance it means they are added. So somewhere the positional flavor or the contextual flavor is getting added to the word. I would like you to think of this a little deeper. As the word is going up the layers in its encoded form, the word is becoming rich with meaning. We call it, the word is becoming pregnant with meaning. The word pregnant is important here because it delivers the next word. We will come to that. But you are making the word extremely rich. As you go up, the knowledge about that word or the word vector becomes rich. So if you realize what attention mechanism works on the principle that somehow enrich the word more and more, refine the word more and reach a point where it becomes so smart that it can predict the next word. So that's actually the heart of attention mechanisms. Now the technique is, how do you enrich a word? What architecture do you use to enrich the meaning of every word? Because unless you enrich each word, you are not going to get anything next out of it. Unless you make him extremely fertile and heavy, he is not going to generate the next word, right? So that's the key. Okay, so going forward, we got the essence of the initial two layers. So let's move forward now into the transformer system. So we have got, now as architectures have changed, have evolved, as I said, we started with the original architecture, This is what is the original architecture. I call it the first architecture. As you study new architectures, as you study Llama, Llama 2, as you study Palm, coming from various companies, you will realize that what they are changing is improving the encoding mechanisms. The basic flavor will remain the same. For example, Llama uses, instead of positional encoding, it uses a slightly different algorithm called rotational encoding. We will talk about rotational encoding when we come there. But you know that gets changed. Or the place where they do the normalization, that changes. Because over time, scientists have experimented over this, realized that if I tweak this bit, I am getting better result for a particular domain. So what has happened over time is this architecture has stayed consistent, but the tweakings have happened to different parts of this architecture very selectively and by different people. And that's how, so you will say, how is Llama 2 different from Llama 1? It's all in the basic building blocks remain the same, but somewhere substantial tweaking has happened to change it. And I'll try and highlight, because why this is important is, tomorrow when we read new papers, people are doing it continuously. You will see how do you convert your own version and why would you do that, right? So it's important to understand, because I am assuming that you guys are not just getting ready to use these engines, but design or adapt these engines to specific domains by making changes. So going forward, now let's focus on what really happens. So we are now ready to move into multi-headed attention. What have we got so far? We have got the original word to vec encoding, we have added positional encoding to it, and now we look at each layer, okay, each attention layer to understand what happens in attention. Okay. Now what happens in attention, or I'll just abstract this diagram a little bit. So I will say what is a building block? There is transformer and there is transformer. And then there are layers and layers. As I said, there are 96 of these in GPT-3, and each transformer consists of basically two significant parts. One is a feed forward, and below that is the MHA, okay, the multi-headed attention. Okay. Now I think so, and you have layers of this. So now let's talk about head of attention or multi-headed attention. What does it mean? Okay. What happens in the attention layer? There is an attention layer, or call it MHA layer, right? I am using MHA or attention layer synonymously because every layer is a multi-headed. Okay. You will understand what I mean by multi-headed. Now here you would like to pay a lot of attention, because here is the key of attention. Are we ready? Okay. So attention has been often very nicely described as a matchmaking service. So you thought it is something more complex. It is not. It is just Tinder. Okay. It's just a matchmaking service. Okay. Nothing more glorified than that. Nothing more substantial than that. Now, how is it matchmaking? And how does the maths of that happen? How does the algorithm of that happen? It's like this. During the attention mechanism, every word vector has built, I told you, as you move up the layers, every word vector captures a lot of information about that word. For example, I mean, I'm just giving you an analogy. As the word has gone further, the word John, which was there, let's say it's a storybook and you are analyzing it. So the word John, which is coming in the 50th chapter or the 30th chapter, are you getting me? Let's say we are analyzing so much of English, and by the 30th chapter we are on John. The John in the 30th chapter, when I said 30th chapter, it is with lot of input has been fed in. John at the 30th chapter knows A, he is male, B, he knows he is married, he knows he is rich, he knows he is lot many things. How did it figure out? All this is captured in those vectors. How does it know it? It's through the churn, through the context. Okay. This is what I call enrichment. The vector knows it has some properties. It has captured some properties. Now you will not, this is all numbers. There will not be rich written there, there will not be single written there, there will not be male written there. It's all in the numbers. The numbers are somehow captured. Remember, there are so many numbers for a given John. So those numbers have captured this information. Now, John and Mary went to a restaurant. Okay, so it knows that John is there, Mary is there. Mary, the word vector for Mary knows a lot about Mary. Okay, and so John went with Mary to a restaurant. This is the sentence. Right? So as the layers are increasing, lot of information is getting captured. So during attention, what happens is, I tell what I am looking for. That means, what is matchmaking all about? Remember, when I say I am looking for means, what could be my announcement in pursuit of what is my next word? Okay, let's keep that aside. I am announcing to the world what I am. That way, imagine each word in the sentence is announcing to the other words in that sentence what they are. No, yes. Then the enrichment happens. First, I announce myself to the rest of the words. Imagine the words are live. The rest of the words are announcing themselves to me. How? By their own individual vectors, through some transformations. The other vectors also have, each vector is given a notional value. Now this is an important point. Now you will ask, how are they given value? Initially it's all random. As the algorithm works, they get values. So imagine each word has a vector and it has a value. Every word has a vector and a value. Value indicates the importance of that word in that sentence. For example, John went with Mary. The words Mary and John will be important. Their value will be more. The rest of the words, which are prepositions or otherwise, don't carry too much of value. They don't have value. So John is announcing itself to the rest of the words. There is a matchmaking happening. Now the matchmaking, what is it doing? It is transferring a piece of the value of Mary to John. To what extent value of Mary will be transferred to John? To the extent that John and Mary are similar. Once again, we are making 2 points here. First point, what we are making? Every word is enriched. Second point, every word has a value. What happens during attention mechanism? I announce myself to the rest of the words. The rest of the words announce myself to me. You are with me? And what happens? If I find a guy or I find a word similar to my word, then a large part of that value, proportional to the similarity, moves to me of that word's value. Similarly, part of my value moves to him or the other word. Why are we doing this value exchange? Because that is how the enrichment of the words will happen. Words will get enriched by the meaning of some other words in the sentence. The words in the other sentence enrich this word, provided they apply to this word. What is this matchmaking for? to see whether that word applies to me, and that much information is transferred. Now, Mary went with John went with Mary to a restaurant. Now, the word he obviously refers to John and not to Mary. Now, it has not been taught grammar of striring, pulling and all that. We are not taught gender. It has learnt all this by itself, that he is saying I am a male, and John is saying I am a male too. So, whatever refers to he, the enrichment which has been given to he, a lot of that enrichment gets transferred to John. So, John becomes enriched because something about him has come from he. You are getting me? So, this is called attention mechanism. Now, how is it done? We will see. But the crux of attention mechanism is there are three vectors. Okay. There is something called a query vector, which is John asking, looking for someone, that is his query. Then every word has its own vector, which is its key, and it has its own thing called its value. It has a key vector, this is extra, this is associated extra. During attention mechanism, this does not stay with the word. During attention mechanism, there is a key associated with every word, this through randomization, and it learns over time. Initially randomization, then over time it learns that with every word, a query vector, a key vector and a value vector. Are you getting me? With every word, that is with every incoming vector, there are three vectors associated: query, key and value. So, what happens during attention mechanism is, the query vector of one word gets multiplied with the key vector of every other word. The similarity, when the multiplication is done in such a way that if there are similarities, the value of the multiplication will be high, that is taken, and value of that word whose key is there, that is taken, and that value is transferred to this original word. Okay, let me try and depict this. This is something interesting which is happening. The transfer mechanism, transfer of importance or enrichment.
The three vectors are done during embedding. When do you
No, they are randomly assigned first.
But who does that?
Oh, the program only does that. These vectors are initially random in the beginning of the learning. But remember, this learning happens over thousands and billions and trillions of words. For example, GPT-3 was trained over 1.4 trillion words. So, by that time, these vectors become more refined. So, let us take one word, let us take another word, and let us take a third word. Let us say there is Q1, K1 and V1, Q2, K2 and V2, Q3, K3 and V3. Now what happens? This query of this is multiplied with K2 to see what is the influence of this word on this, and the result of this multiplication, which is generally a dot product or some artifact that we, some gadget or some technology that we use between Q1 and K2, generally a dot product on the transpose, that is what we do. So, we do that. The similarity between these two decides what portion of V2 gets transferred to V1. Here. This is how the attention mechanism works. Now, why is it logical? Because see, this word has captured a lot of value that is reflected in its value, okay, the value of the word, what we have right now. The query vector only defines, is also taken from this word itself, and it decides what is the enrichment I have had so far. Now I am getting associated with you, so this is your key, that is your key vector which symbolizes your identity, and V2 is the value you have, and these are all worked out for every vector as it passes. This gets transferred here. Similarly, transfer happens from here. How is that? Q1 K3 times V3. So, the equation which they use Q1 or query dot key transpose of V, V refers to this V, and then there is certain amount of normalization which is square root of dk. Dk is the dimension of the vector of all these vectors. They are the same size. So, in our case for GPT-3 it is that 12,288, you take the square root of that. That is only to bring the values to a normal thing so that values do not escalate too much and we have problems like you have the vanishing gradient and exploding gradient. To reduce that we divide it and then we do a softmax on this and use that value to bring this here. So, this is the equation which happens, but in short what is happening is that the attention is being shared from other words into this word. Now, I do not know how many of you took it. Any question understanding this? These vectors evolve over time, they get refined. You must have seen in the CNN, we start with certain weights in the beginning and those weights get altered as we go. So, these vectors also are going to change over time. As a system is going to learn, these vectors are going to become more and more smart, right, in addition the original vector.
So, but how is there a relationship between the words if all of the initial values are random?
Initially it will go wrong. So, what will happen? Just like you saw in a CNN or an RNN, it will make mistake, there will be a feedback and then these things will change. See, this is not happening, this is happening with trillions of words. So, this whole changing will keep happening in a very dynamic manner. Initially, and I will give you some examples as I go on, initially everything will be random or largely random and there will be no enrichment, but as we learn more and more, these weights start beginning to stabilize. These Q1s will stabilize, the V1s will stabilize, the K1s will stabilize. It is over time. Think of this if you will, and that is why we had those sessions with a CNN. You have those weights, those the weight matrices, how are they started? They start random and then they start learning. So, it is the same thing, otherwise this would not be an AI topic at all, right. And that is why you wouldn't need those 2100 GPUs churning out that data. This is the power. Now, this is called attention. This is the attention mechanism. Now, what they have done is they do not use one attention mechanism because they say just like there is matchmaking which Tinder does, there is matchmaking which LinkedIn does. In Tinder, you are giving a different profile and you are getting enriched in your profile differently. In LinkedIn, you are talking about your job, what are your skills. Nobody talks about I am single, I am rich, no. That you do in Tinder, you do not talk about that in LinkedIn. LinkedIn you say how skilled you are, how many people think how great you are, the fact that you went to KMIT, adds value or whatever, right. So basically the point I am making is there is no one attention mechanism, meaning there is not one set of Q1, K1, V1. There are many Q1s, many K1s, many V1s. So, these are very different. Each is called a head. Different kinds of matchmaking and different kinds of enrichment happens. I hope you are getting that. It is not one kind of attention. How do you define one attention? by one set of keys Q1, K1, V1 for one particular head. There is another set of Q1, K1, V1 for another head and for another head. Just to give you an analogy or just to give you a thing, do you know in GPT-3 how many heads are there in each layer? There are 96 heads. There are 96 heads and 96 layers. So how many times attention is shared or this learning happens? 96 into 96 times. That many sharing events of information happen during the whole system. And this is for one sentence. Are you getting it? So there is so much of refinement which happens. So there is 96 heads in each layer, and imagine there are 96 layers. So there is so much of enrichment. So as you go up, the words start getting enriched and enriched and enriched. So okay, I will give you an analogy. How do these words start getting kind of enriched? Okay, I think I'll give you an example and then I'll give you another example later. So here is how it happens. So look at these two sentences. John took Mary to a restaurant. He bought now what should come here? This is the thing. Now if you look at this sentence, John took Mary to a restaurant, he bought a drink for. Now the system has to decide what should come there. Should it be John? Should it be Mary? Or should it be something else? Now by the sharing of this attention, they say by the 40th layer or 50th layer, it is able to get this right, that the word which should come here is Mary. Now it's not so easy. You may say, what is there? Obviously, this is not so easy because first of all, he bought a drink for whom? Now you will say there are only two people involved in this sentence. Isn't it obvious? It's not. First of all, buying drink is something else. Whether it should be the same person, whether the two people you went to the restaurant, one of them has to be bought a drink. This is not common sense for a large language model. For you and me, it may be, who else will he buy a drink? Obvious. Now, but the system has begun to think that it has realized that it is Mary and not John. He can't buy a drink for himself. So when they analyze this, they realize there are about 9 attention heads playing in this game. There are 3 attention heads which suggested that there has to be a name which has to come here. 3 attention heads decided that there is a name which has to come here. 2 attention heads decided that it should not be John, and some more attention heads decided it has to be Mary. This required interplay of about 9 attention heads through the various layers to realize till the 40th layer that Mary should come here. Now you see this sentence. Then I will give you another sentence. So John took Mary to a restaurant. Let's say instead of this I said he gave his keys to, and I have to guess the next word. Now it's obviously not Mary. You don't give keys to Mary, right? Now the word there is valet. He gave his keys to a valet. Now it's not John, it's not Mary. This requires up to 80th layer. Are you able to get? At 40th layer you can't figure out. At the 40th layer it would be either John or Mary there. as more enrichment happens, as more information happens, then it starts realizing, oh, no, none of these two people are involved in giving key. The person who needs to have a key is a valid. This happens by the time you are at 80th layer. Getting a hang? This is called multi, and there are different kinds of associations. Here there is one-to-one association. For example, just to say Joe Biden is the President of America. Joe made the following statement. Now here Joe is part of that Joe Biden. Requires sense. This doesn't happen at the second layer, or this doesn't even happen at the 20th layer. This needs again 30-40 layers up before this realization happens. So this is called multi-headed attention, and I hope you are able to understand the mechanism, the maths which happens is the Q, K's and the V's. The technique is what? Enrich each vector by querying other vectors, finding out their key values and transferring some of their information to us. Correct? Some of their vector gets part of us. By doing that, we do this. Now this is called MHA, and there is one more point which I want to point out at the MHA. See the deep link between multi-headed attention and power of computing. See, while the query mechanism is happening, if you ponder over it a little bit, if you think a little deeper in this, how the query, key and value transferring is happening, you see this is completely an autonomous operation. That means what I am trying to say is, while one word is doing this, it does not inhibit or prohibit the second word from doing something similar. No, yes. While I am getting attention from the rest of the people can get my attention because I have my Q, I have my K, I have my V. They have their values. So, do you understand where now the GPU comes in? Because GPUs, what do they bring to the table? Typical GPU has, our one A100 GPU has 48,000 cores. That means potentially 48,000 threads can run on it. Each thread can be doing one Q, one K, V with some other Q, K and V. And all of these threads being GPUs, they are extremely adept and extremely fast at doing matrix multiplication. Essentially, how is this happening? It is through matrix multiplication. You are multiplying your vector with a Q or a K or a V. V is not getting multiplied, V is getting transferred, but getting multiplied and transferred. So all this is matrix multiplication, and each thread can happen on a different CPU. So the computing for one layer's multi-headed attention can happen completely independently of anyone else, and that lends it supremely competent to use a GPU. That is why this has become possible. Now you have to understand this, because if you try to do this without using a GPU, the next 300 years you will be here, right? But with a GPU you can do that in a jiffy, and that jiffy also means a few months, right? These machines can be trained in a few months to do all this. Why? Because you have immense compute power and parallel. The emphasis and underline the word parallel, because that has made this possible. Today, or till the last few years, the world has moved, or human civilization has got that kind of compute power which has made it capable. So that is the crux of multi-headed attention. Shall we move on? Everybody clear? Reasonably clear. When you work with it a little more, you will get this, but you should understand that there is this transfer. Q, K and V are primarily mechanisms of transfer. I have written the equation on the previous thing. Q into K transpose multiplied with V divided by root of dk that's the seminal equation, that's the fundamental equation by which information is transferred from other words, other vectors to this vector. So that's how vectors keep growing. Now, they looked at two aspects. One is each vector is sharing information with each other and all that is happening, but it's all happening within the words. So far, the attention layers focus on enhancing my attention or my value or my vector by whom am I associated with. That means when I am doing the attention mechanism, I am seeing how I influence the other words and how the other words influence me. I am looking only at that. Okay. Now, attention mechanism only is about sharing and going both ways. I share my value with others, others share their value, I get enriched. So, enrichment is through that. Now, I told you in every transformer block there are two parts. One is you have the attention block and then you have a feed forward network. So, what is this role of this feed forward network? Now, feed forward network looks at every vector by itself. It forgets about who are the neighbors. That has already happened. At every layer it is happening. And at every layer there is gathering of attention from the neighbors from whom I am keeping company and also my self enrichment. Okay. Now you will say, what do you mean by self enrichment? What is the actual role of that the feed forward network? That is the second half or the upper half of that transformer block. There are two halves, right? The MHA and the feed forward block. So, feed forward block, think of it like that. It refines the meaning of this vector by itself, by not looking at others, but then you will ask, how does it refine itself if it is not looking at others? Now it starts looking at the corpus of information which has been gathered. So, I told you the word valet was not in the original sentence. The word valet came from outside. That is, it means that it was not the attention mechanism which brought valet. John went to a restaurant with Mary. He bought her a drink. Here, the information is self-contained. He gave his keys to would not happen if you turn off the fact that there needs to be a valet there will not come, because valet relies on corpus. It is not attention within, it is attention without. Without when I say it means the attention or information or enrichment is coming from the corpus. So it has figured out a way not only to learn from others but also from the corpus. And it is very nicely segregated, if you will. The lower layer learns about others through various heads, various information. And the upper layer learns from the corpus and enriches this one. So, are you getting this? There are two kinds of enrichment which are happening. Enrichment by company, enrichment by self. Both these enrichments of the word keep happening. And ultimately, you know what has to happen? Ultimately, the last word in the last sentence has to get enriched to a level that it can predict the next word. What is the purpose of enrichment? Is to add so much of enrichment to the last word of the last sentence. So far, whatever is the last sentence, to the last word in that last sentence, so that it can predict the next word. That's how the next word comes. That is what they say. Make the last word so pregnant that it will deliver the best word next. Last word in the last sentence. I hope you are getting the impact. Corpus enrichment comes through accessing database, all that kind of thing. Again, I will give you a small example. How the enrichment actually happens and what was observed. Okay. So,
Okay, here is a prompt. Hyderabad. Now this is the prompt and this is the query. You can think it's a prompt itself. The complete prompt is Hyderabad is the capital of Telangana, and what is the Hyderabad is the capital of Telangana, and what is the capital of Karnataka? I am asking this question. Now it so happens. Okay, now look at this sentence. What happened? This is observed. Okay, this was experiment done with GPT-3 and GPT-3. Now what happened is, till I believe the 30th layer or 35th layer.
If you say what is the capital of Karnataka, it was saying Hyderabad again. You are with me? It was only looking at attention. And then at 35th layer, till 34th layer, it was saying Hyderabad. No, sorry, it was saying Karnataka. I am sorry. It was saying Karnataka only. What is the capital of Karnataka? Karnataka. It was saying that. It figured out it is something to do with state. It figured out that somewhere we have to say some state, something related to state. This was still 34th layer, or I forget exactly, but let's pretend it is 34th layer. It was able to say it is Karnataka. It said Karnataka. Are you with me? Before that it was all random. It was saying something not related. By 34th layer or 30th to 34th layer, it was saying Karnataka, 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 Karnataka. Now what happened is, somewhere around 35th layer, it figured out, oh, it's not Karnataka, it is Bangalore. So at 35th layer, it figured out it is Bangalore. Now what they did is something interesting. This is important. What they did is, they observed the change in that vector of that word, because the word was enriched, right? They observed the enrichment in the word Karnataka, okay, was enriched by some vector, and then it became Bangalore. That some vector was added. So they took that vector. Are you with me? They took that vector which was added it to China, and they got Beijing. You are with me? Again demonstrating that how the vector arithmetic is being learned. We talked about vector arithmetic being there. So a lot of vector arithmetic is learned during this process also. It starts with certain vector arithmetic, that is standard. But it is also learning a lot of stuff and bringing it back and enriching it. So it said that if you add this vector to China, you are actually getting Beijing. So it has learned how to jump from a vector for a city or a place to its capital. That change is there. That triggers the change, and that is how the difference of the vector. So if you add that difference to this vector, it was getting the original. Now this is very interesting because it gives you an insight into how these things are changing, how these things are evolving. So essentially we talked about two parts. We talked about multi-headed attention, and we talked about getting the feed forward network. So again I will repeat, multi-headed attention, others. Feed forward, refinement. Refinement via corpus or database. There have been substantial changes as this architecture has evolved. How do you look at a database? How do you refine using a corpus? All that has happened. Okay, again at this point I will tell you, though I just talked about multi-headed attention being an extremely fast and a GPU operation, the way it was proposed by Vaswani and all in the original paper is not used in any of our current systems. It has been modified again, and when I talk about Llama, I'll talk about how the algorithm for computing MHA, the basic algorithm is the same, Q, K, V multiplies all that. How it is done, we'll learn from a parallel programming perspective how they have optimized it. How they have done, which is some of you will know, they have used a concept called checkpointing, which those of you who are familiar with databases will be aware. So they took that concept from checkpointing. Do you know what is checkpointing in database? It is when a database is going on, when you want to recover, you start from the last checkpoint and move forward. Same way here, lot of things are saved by doing very intelligent checkpointing. Of course, the checkpointing done here is a little different from, lot different from what you see in databases, but similar concept has been engaged. This made them even faster. So that's how they could grasp more things and all that. Okay. So coming back to the original paper. So we just talk, this I think we'll send it to you. This is how the story happens. Now I'm not talking too much about the decoder because the decoder is exactly similar to the encoder, only thing is it doesn't see the whole sentence. It sees only part of the sentence and predicts the next word. Otherwise, conceptually, encoder and decoder are exactly the same. There is no architectural change. The transformer is the same. Next. So a bit of maths is there. So they show you how to do the maths. That is the key vector, the value vector, all those are linear vectors. Come down. Linear transformations, the query key value. This paper will show you the maths of how that happens. Basically, as you can see, it is matrix multiplication. You take the vector, multiply it, get all that. That you have been seeing in CNNs, you have been seeing in RNNs. At the end of the day, it's all multiplying matrices, and that's why GPUs are supreme. Next. Okay. So this is where this paper goes. Next. Okay. Now, there are certain fundamental ideas, and then there is, if you go back to the original diagram, there are these layers of normalization and closing the end. Those are all computer science concepts. They are used to, you know why normalization is done after every layer, basically to get all the data to stabilize. Those, again, there has been changes in the way normalization is done. There are between each layer activation functions which will come in. We'll talk about this in detail when I talk about Llama, where we'll focus on the architecture and how it has changed. So there are, I have skipped the add and normalize layers at the end of it because they are nothing value. They are just mathematical computations. They don't bear any semantic sense to us. So going back, you know, there are a couple of things which I think you should know from a architecture point of view, where GPT-3 and GPT-4 are still struggling. Now, I will give you a paragraph. Okay. Listen carefully. Listen to this paragraph carefully. It's a 5-6 sentences. Listen to all of them. Okay. So, there is a bag of popcorn. I am repeating. There is a bag of popcorn. This is the sentence, paragraph. There is a bag of popcorn, first sentence. Second sentence, there is no chocolate in it. The cover of the bag says chocolate. 3 sentences so far. There is a bag of popcorn. There is no chocolate in it. The cover of the bag is closed. The cover of the bag says chocolate. Mary finds this bag. Mary has never seen this bag before. Mary doesn't open the bag. Mary has never opened the bag before. Never seen the bag, never opened the bag before. Mary now opens the bag. She expects to find dash. Now, it's not so easy. The correct answer is, of course, she expects to find chocolate. But if you ponder over that sentence little more, and look at its semantic sense. Now, you have to think a little. If you look at it from the semantic sense of the sentence, what will it say? Popcorn. But if you, what will really happen? She will think it is chocolate. Now, how did GPT-3, not GPT-3, GPT-3 fails. You give this to GPT-3, more likely than not, or in some probability, there is this game of probability, it will say popcorn. Because it has goofed up on the semantics. There, we go into a world where we leave computer science and talk about psychology. It's called computational psychology. So when you talk and look at it from a computational psychology perspective, the answer is chocolate. But if you look at it from a semantic perspective, it is popcorn. She expects to find what? If you think semantically, popcorn. If you think, this is where they call, where they say, now what is happening with GPT-4 is the theory of the mind. What does theory of the mind mean? That it has started thinking like you. It says chocolate. She expects to find chocolate. GPT-3 or an older GPT will say popcorn. Because it will look at only the semantic sense. It will not go into a human sense. That has been because a lot of more learning has happened. Another incident. This is a real life, so I'll quote it verbatim. GPT-3 again failed with this. What they did, all these generate excellent code, right? So they said, generate the code for drawing a unicorn. They told GPT-3, generate a code for drawing a unicorn. You know how unicorn looks, no? Looks like a buffalo kind of thing or whatever with a horn. The horn is prominent. For a unicorn, the defining thing is the horn at the top. Yes, no? So draw a unicorn. So it created in a particular library, they asked, so it generated code. Now this is interesting, please listen carefully. They generated the code. It gave the code for a stupid looking unicorn, whatever. The code was there. But the code worked, and if you run it, you see an animal with a horn. Now what they did is, manually, they edited the code for the horn out. They edited the code for the horn out. They removed the code. And they said, now add a horn to this unicorn. Again, they ran the code and they said, add a horn to this unicorn. So they had the original code, sorry, not the original code, the edited code which had removed the unicorn code and said, add the code for the horn, and it generated the code for them. Again, this is the thinking mind. It saw, see there are 3 or 4 things happening here. I'll summarize it. It saw that this is the code. It saw this code does not generate a unicorn or does not generate a horn. It picked up what is the code for doing a horn and it added that code at the right point to get back the horn with the unicorn. This is thinking. Now this was not possible in GPT-3. It became possible in GPT-4. Again learning. And they say the thing which was responsible is basically the addition of the corpus and running it on a more powerful thing. Architecture didn't change much. Of course the layers increased. That's not change in architecture. Okay. So this is the short and long of what is attention. Attention is all you need. Now I have tried to give you a non-mathematical and a mathematical picture, but I hope you got it. I don't know how many of you got it, but I'll pretend that a lot of you got it. Okay. So you have to read the paper again, and you will not get it again the first time. You have to read it again, and again you won't get it. Again read it.